Here is another special case of factoring quadratics. It's known as factoring a difference of two squares. But let's make sure that we remember how we distribute and what it looks like, what happens whenever we have two binomials where our constants are opposite in sign. So when we distribute the x, we have x squared plus 2x. And when we distribute -2, we get -2x minus 4. We have four terms, but when we combine, notice our b value is going to be 0, and we're not going to have a linear term. We have x squared minus 4. Our next example, we have x plus 4 times x minus 4. We get x squared minus 4x plus 4x minus 16. When we combine, our b value becomes 0, so we have no linear term. And we have a binomial where both terms are perfect squares and the operator is subtract, just like in this first example. Our first and last term are perfect squares. Our operator is minus. There is no linear term. We have a quadratic term and a constant. Our last example, 2x plus 3 times 2x minus 3. The result is the difference of two squares. We have a quadratic term that's a perfect square, a constant term that's perfect, and our operator is minus. We must have subtract in order to have a difference of two squares. Difference, subtraction. So here we have a quadratic where we have the difference of two squares. There is no linear term. This is only for when we have no linear term. We have subtraction, and our quadratic and constant are perfect squares. Again, if you don't recognize that this is a perfect square, the difference of two squares, if you do not recognize, you can still use the grouping method. So let's do this with a shortcut, and then we'll take a look at it when we do the grouping. So we're going to take and factor our quadratic into x and x, and then we're going to factor our constant into its perfect squares. One must be minus and one must be plus. It doesn't matter the order. We need opposite operators so that we would have no linear term, no b value. Now let's say you didn't recognize this. Our a term is 1, our b value is 0, our c value is -81. We have a times c. We have our b value of 0. The two numbers is going to be -9 and +9. When we rewrite, we get x squared minus 9x plus 9x minus 81. We're going to group the first two and the last two. We're going to factor out the greatest common factor. And we're going to group the GCFs and the common factor. And you see we have the same result. In this example, we first need to factor out the GCF of 2. Once I do this, I'm going to recognize that this is the difference of two squares. I have subtract. My quadratic and constants are perfect squares. I'm going to just set up for my two binomials. You factor x squared into x and x. You factor 225 into the two perfect squares. One must be plus and one must be minus. X squared minus 196 is the difference of two squares. I do not have a linear term. I'm going to set up and I'm going to factor x squared into its two perfect squares as well as 196. One needs to be a plus and one needs to be minus. In this example, we have a GCF, and I believe 144 is divisible by 9. It is. So I'm going to factor out 9, and I'm going to have x squared minus 16. I have the difference of two squares. I'm going to set up my two binomials. I'm going to factor x squared. I'm going to factor 16. One needs to be plus and one needs to be minus. This binomial has three factors, 9, x plus 4, and x minus 4. Here we have the difference of two squares. It doesn't seem to be a GCF. So we are going to simply get set up. This is where I would not want to use the grouping because I would have very large numbers to work with, and I would definitely want to learn and be able to recognize the difference of two squares. Again, there's no linear term. You have a quadratic term and a constant. So I'm going to factor 16x squared into its two perfect roots and 361. One needs to be plus and one needs to be minus. Order does not matter because we have commutative property.